Okay, how's everyone doing? That it? 50-50? Yeah. I forgot to mention Tuesday was National Register to Vote Day. Everyone here can vote, maybe? Kind of? Have you registered? Have you ever voted? You believe in voting? Civic duty?
Yeah.
No, I hate jury duty too, right? Ooh. No, participating in civics is good. Okay. If you say to yourself, well, I'm not really that interested in politics, that's okay. Just let other people make decisions for your life. You know. And remember, of course, some of the decisions that are important are like whether or not minimum wage is good, whether or not you should have like a weekend, whether or not you should be protected in your daily life. These are all decisions that if you don't want to participate in politics, perfectly fine, but you don't get to complain, right? So the only way you make your voice heard is by registering to vote and then voting. And in California, voting for the president basically means nothing, right? Because they're gonna win, right? This state, no matter what. So who do you vote for? You vote for governors. You vote for state senators. You vote for state assemblymen or people. So I would go and I would do research. Find out who shares your views. Because local elections matter much more than national. Okay? That's my only politics spiel of the day. Okay, baseball, good. Elections, good. Homework? Good? Everyone having fun still? No one's dropped? One person has not given me anything. Hopefully they give me that today. Other than that, I've seen participation from everyone. That's good. Any questions before we jump into lecture? Okay. Let's see if this works. What's this? Mountain. Good. Correct.
Is it sandstone?
What?
Is it sandstone?
You're asking what type of rock? No, not quite sandstone. Yeah. Half Dome. This is in Yosemite, so you can go there and you can climb up this thing. There's like a little rope chain. And if you fall, you can fall to your death. It happened recently. Fun stuff. This is granite. And this was at some point a full mountain. It had a full rounded peak. Anyone know what happened? Yeah.
Would it be a glacier?
A glacier eroded it. What's a glacier? Ice. Long, big time ice. Went and cut right through the mountain. Just cleaved it in half. Okay? Hence half dome. If you have ever worn something that says the north face, the north face of Half Dome. How do you know? I also like this picture a lot because it has clouds. I love me some clouds. And these are a special type of cloud called lenticular clouds. They form on the top of mountains where wind like rushes up the mountain and it cools as it goes up. And then it creates these like little pockets of cold and hot. And so you see there's these little pockets of cold and hot and they get bigger and bigger until they're all cold. Cool. We'll talk about clouds in detail later. Okay, next week, I promised you no tests. We will not do a test, but we will find out how you're doing. You will assess your own confidence in the material. You will exceed, you will meet, or you will fail your expectations. You have a personal education goal. I want to know what that is. I want to know how you're doing, and then I want to see the evidence for that. If you want feedback, like what can I be doing to get better, I can give you that. I may give you unsolicited feedback, which says like, I agree with these points of your statement, but I think this could be improved by X, Y, Z. Okay, so on Tuesday, I'll release a little thing that writes up exactly what you'll be turning in, what I expect from you. And then the following Tuesday, So not next Tuesday, but the one after, you'll hand it in. You'll also include everything you've done that's been graded. So if you have homework 1 and you got it back and it was really good, great, include that. You got it back and it said write more, please, and then you wrote more and that got graded as well, include that. Okay, that's all evidence of your success. Cool? Okay, this is gonna be really rough for me because I'm gonna have to read 80 of them and compare all these things, but I'm trying it because I want you to succeed. Questions about this? Okay, it's in the future, so no one cares. All right, next one. How is the homework? Okay, let's find out. This is a silent poll. Don't ask people. Don't game the system. Try to make it easier just because you're like, oh, this is a pushover class. Yeah. Oh. Can you write it down? Thank you. Okay. About 45 of you clicked in so far. 50. Anyone else want to click in who hasn't? 53, 54. Final answer. Okay, 3, 2, 1. Okay. We were talking about the 4 processes that shape planetary surfaces. You got 3 of them already. You fully understand volcanism. You're all experts in identifying volcanoes. You know that the Hawaiian Islands are what type of volcano? Shield. And shield just means really runny lava. So the stuff just like comes out and goes everywhere. So you got volcanism, experts. You got impact cratering. Now when you look at the moon, you have this new felt appreciation. Like, wow, that thing's been beat up its whole life, just like me. Right? You got tectonics. You know that because you live in California. You've been raised to know that the earth shakes. Because we are basically floating on rock that floats on magma. So if you look down, that's the only thing between you and many, many miles of lava, right? Okay, so let's do the last one. The last one is erosion. And these are surface changes due to wind, weather, or ice. Okay, so we saw an example at the beginning of class of the ice. We'll see examples of water, like this one here, the Grand Canyon, famously, and wind. Wind, a weird one. Do we have an example of an erosion process with a wind? Sand what? Sandstone, okay, sure. So that, you could start with sandstone, which is a type of rock, right? Yeah. Sand dune, right? Sand dunes are actually sculpted by the wind, and they move. Did you know that? Sand dunes all move with the wind, very slowly. But like if you were on God mode and just sitting there, you'd be like, "Woo, cool." Make sense? Okay. These are these examples. Sand dunes in your bottom left-hand corner. Grand Canyon, I think. Oh, that's the one I already showed. That's right. Okay, so this was just perfectly good granite, just living its best life. And then a glacier was like, nope, and just cut directly through it. So this is a beautiful valley, the Yosemite Valley, that's carved by ice. And this is a beautiful valley carved by water. And then you have similar processes here. This is not quite carved in the way that we think about it, but this is a river delta. And sometimes when you have changes in the slope, like how steep the ground is, you can get material to deposit itself. You can get modifications even from rivers that aren't like flowing for a really long time. Maybe just depositing stuff is going to change how the ground looks. Okay. Okay. Does Mercury have these features? No. Does the moon have these? Does Venus have these features? Yeah.
Yeah.
Okay, interesting, interesting. Does the Earth have these? Yeah, okay, we got that one. Mars have these. Which of these features? What? This one? Does Mars have this one? Interesting, interesting. All right, all right. This one? Okay, okay. This one? This one. Yes? Okay, all right. So we're not reading ahead. That's okay. All right. Those are all the words that I just said. I guess I should put that at the same time. My bad. Let's talk about the definition of erosion. So this is the process of grinding down the surface, grinding down the components of the surface, whether that's rocks, whether that's yeah. For the purposes of this, we're talking about planetary weather. So there's versions of erosion that come from like impacts deforming the surface on the moon. That's called micrometeorite gardening. That's not what this type of erosion is. Okay, that's outside of the scope of this work. This is only thinking about wind, water, and ice. So yes, one of the necessary components is to have an atmosphere, because you need, for example, wind, you need gas, right? So you need something that's moving around. And if you have water, you need it to be in a liquid form if you want water erosion. It's okay to have glacier as long as you don't care about rivers, right? Okay. You need rotation to cause weather. And I'll explain this in more detail when we start to talk about the atmosphere as a whole. But right now, let's just trust me, okay? If you are rapidly rotating, you get more storms, you get stronger weather patterns than if you're more slowly rotating. There are some caveats to this, but what I mean by this is that if you're not moving very fast while you're rotating, then you might not have winds at the surface. So, while Venus has a very thick atmosphere, as we'll see later, the surface winds are almost zero, because Venus is extremely slow at rotating. Its year is about the same as its day. Okay? You need liquid water, which is a Goldilocks problem. So if I get too close to the star, it's too hot and all the water boils off. And if I get too far, it's too cold and all of it freezes. So if I want liquid water, which is the best at creating erosional features, then I need exactly that range of temperatures in which water can exist. Okay? Okay. What's this?
Sand dunes from above.
Sand dunes from above. Very good. Sand dunes from above. So this is sand, and these are dunes, and the light is coming from the top, and so these are shadows on the backsides of the dunes. You know where? On Mars. Correct. What are these? Also sand dunes, good. What's this stuff? Excuse me? Yeah, it's something, some form of darker sand, sure.
Sulfur.
This is all still sand. There's no rocks and well, there's no big rocks in this image.
With a feeling child.
Not quite. Yes, this is remnants of a certain type of wind feature that exists on Mars. It exists here too, but you probably didn't know they existed on Mars. Very close. Smaller. Dust devil. Have you ever seen these?
Only in videos.
Okay, so sometimes you get really small ones, or you're just like walking around, and maybe you're walking by a part of the building that has like an L in it, and the wind blows in, and you see all the leaves go around in a circle,
Oh, yeah.
and it like goes up into a little bit, and then it falls all back down, right? So that's what these essentially are. They're basically places where the wind is swirling around, and as it does, it picks that material up and turns it into a little plume. Dust devils.
Okay.
Yeah.
So what was the, you know how you said it was like sort of like a spinning over the 2 months here and
So what's happening here is that this is all sand, and then a dust devil comes along, and as it's moving, it picks up the top layer of sand, showing a darker layer of sand underneath. Right, mixing it up. And then the rest of that is taken off by the wind, blowing away. So 2 things that we've learned today. 1, Mars has an atmosphere. That's pretty cool. And Mars has a strong enough atmosphere to pick up dust. So it can have erosional features similar to the ones that we see in windswept areas. All right, what's this? Also seen it's very good. In with the right answer. Where? I hear Sahara. People know about the Sahara sand dunes?
I was gonna say Arrakis, but I know anybody's gonna get.
Solid reference.
I have the book too.
Yeah, these are. I got that last one. I got that last one. Okay. No, is this so? This is on Earth. Everyone's confident. I just showed you Mars, right? This is not Mercury. Why is it not Mercury? Mercury doesn't have an atmosphere. Mercury doesn't have sand, right? We never landed on the surface of Mercury. That's really important. This is clearly taken from some dude standing like here, right? Are we sure this isn't the moon and I like colored it to be tricky? No, moon also doesn't have sand dunes. Okay, no erosional features on Mercury, no erosional features on the moon. Venus, can we stand on the surface?
Oh.
It does have a hard surface, but the surface temperature is about 700 degrees, which means that the longest that we've had anything survive without melting is close to 40 minutes. Everything else just melts. So no, you can't take a good picture like this. What's that? Yeah,
I didn't know.
yeah, we'll get there. We'll get there.
So this has to be either the Earth or Mars.
Right, okay, we've narrowed it down. So where? Raise your hand for Mars. Raise your hand for Earth. Okay, all right. The Earth people win. Which continent? Yeah.
So,
Ooh, interesting. What? No, it's not. I like where your head's at. This image is cut off. I'm hiding something. Yeah.
I don't know where it is, but I know what you cut off.
You know what I cut off? Oh my goodness. Okay.
Because I'm not-
It is a mountain. Those are the Rocky Mountains. And this is in Colorado. That was funny. Some of the tallest sand dunes in the world are found at Great Sand Dune National Park. And the reason for that is sand blows across the US. And then it runs up to these mountains and it's like, well, can't get over that. And so it's all deposited right here. Some of these are as high as 700 feet. And so you can go out there on not too hot a day. You can bring sandboards and you can literally snowboard down them. I mean, it's not snow, but you get it. Right? Yeah, sandboards. You have to strap in, otherwise. Cool, pretty rad, right? Did you know something like this was? You don't even have to go to Sahara. You can just fake it right here. Okay. Mars has water. Mars does not have liquid water on its surface. We find water in a variety of forms, and I'm sure you've seen some like news press release that says we found water in this form. Like, I think I saw that last year. We probably did. Each time we find water, there are nuances, there's reasons why it's important, but that gets lost in news reporting. They just say, wow, everyone's like, who cares? Here's some of the evidence up here for ancient water. You recall when I showed you erosion features, that there was these things that look like streams that were depositing material, right? They're called fluvial features because they look like fans. And this is a place where there was probably a number of ancient rivers, okay? And they all fed in to this river here, and then they deposited material elsewhere. Up here, we can see what looks like that fan I was talking about earlier. As it changes slope, it deposits material, changes the surface structure, and it looks like it's all like curved and stuff, right?
It's like a fossil.
What?
A fossil.
Yeah, but these are big, right? So these are from space. So this is like several tens of kilometers wide. Big, but yeah, it does resemble that. These ones are impact craters. So they smash into the surface and they have raised edges. And then after the impact crater, something really weird happens. Anyone know what that is? Yeah. Not in this particular one, but certainly they're all looking at this example. Let's say we punch into the surface, we raise the crater walls. What leads to these shapes? Geysers? Not quite. These are also really big, so this would be like a kilometer wide. Interesting. So you think there's water here? Why?
It's soft on the edges, like you've been growing
Uh-huh.
big spaces,
Uh-huh.
and they're just massive.
Yeah, they're like really massive, and it's like rounded on these edges here, right? Do you notice that this one is like a teardrop? Does it remind you of like a rock in a river? And the water would pass around the rock. So this happened in an ancient riverbed, punched some holes in, and then water went by. And you can see it pressed around these craters. And then once it was dry, then you smashed these little ones. That make sense? We can tell a little bit about the surface history here. So impact craters can occur and they can get washed away. Sometimes if they're big enough, they can leave really interesting remnants that show that there was liquid water on the surface. There's some other evidence here. Basically these different types of stones that you find on Mars. These are from the Mars rovers, like driving around. There's nobody in them, but they pick up rocks and they'll look at them. And like you have these cool looking rocks called blueberries because they look like blueberries. We're really good at naming stuff in science. And these are formed because when rocks tumble in a stream, are they jagged or smooth? Smooth. If you've ever gone hiking, you go pick up a river rock, the edges are always rounded, right? Bingo. These rocks form in stream beds, rolling, not form, but the shape that they get is from the fact that they're in stream beds. Does that make sense? And then this one's here is really recent. This is cool. This is video of something. I'm not going to explain what it's called, but basically what's happening is you're looking down from above, and this is like the edge of a cliff. You see that? Okay, and then there's a slope. And at the edge of the cliff, you can imagine like layers in a cape. Imagine there's a layer in the cape that's got ice in it. And as it's seeing the light for the first time, it melts. and it runs down the edge of the cliff. Does that make sense? So this is flowing, not really flowing, it's not liquid in the way that we think of it about it. It's very salty liquid that's moving down the edges of these cliffs. So erosional features are happening today on Mars. Okay.
That bottom photo with one.
Yeah, this one is a number that I've taken recently. I don't know if I have the year on there. Yeah, no, that's not them. Those are the image numbers. I can find out exactly when that is. I think it was 2016.
On some papers, I sort of remember reading something that, because the moon is having erosion, all the rocks are so sharp and jagged, to the point where when you land there, it's literally like shredding the actual suits and everything.
Yeah, I don't know how dangerous it was for the suits, but I definitely know that there's really, really fine dust on everything. And because there's no erosional features, every step that we took is there forever. So except for the places that we used the rocket to go off and it blew away afterwards, you went on a little expedition, your feet, not mine, but their feet are still there. There's places that you can zoom high resolution imagery of the moon, and you can see the locations of the landing sites. You can see all the debris we left. We're just like the opposite of leaving no trace camping. Okay. We wanted to leave a trace, so we put flags and shit. Okay. The flags blowing in the wind, is that something people understand? There's no wind on the moon. How'd they do that? Well, it's still going to be pulled down, right? Because the gravity will want to, just when we drop the feather and we drop the hammer. So how did we get it to stay up? Yeah, we just stuck a wire like this and we hung it. So it's like an L shape instead of just a pole. You just hang it like that and you clip it. Right? That technology is not hard. Okay. So that's it. Now you understand 4 ways we deform surfaces. Okay? Questions? Okay. So we started off by understanding how surfaces are deformed. How are they changed? What are the processes by which we modify them, right? We saw the evidence that exists throughout the solar system. And now we have to come up with a model for understanding why they are this way. What are the properties that the Earth has? What are the properties that Venus has? What are the properties that Mars have that make them all so different, right? And eventually this is going to lead us to questions like, why can the Earth harbor life? I think most of us are alive, right? But Venus apparently not. Why is it that there is water still here? And for Mars, there was water, but apparently not anymore, right? These are the questions we want to ask. So we're going to build a model to understand these questions. That good? Okay. Let's talk about a planet. That's us. Not for real. Okay. We live out here. I gave you the analogy that if you take a basketball and you put a single piece of paper on the top of the basketball, that is the thickness of the whole atmosphere. So you live at the bottom of that tiny piece of paper, right? Very small, okay? Most of the planet is magma, is lava, below your feet. You're living on this little tiny crust. Okay. And sometimes it's thin, and magma comes through, and we call that. Come on now. Volcanism. You take molten rock, magma, bring it to the surface. Molten. Good. So you take hot, bring it out. It gets cold, becomes a rock. Okay. So if you define things by their composition, you have the core, and that's the heaviest stuff, the metals like iron and nickel. That goes right down to the bottom. Okay. In the middle, you have this stuff called silicates. You've heard of Silicon Valley. Same element, different uses. Okay. And at the very top, you have the low density rocks. We talked about granite at the beginning of the class. What was the example of granite? What? The very first slide. Yeah, what was that a picture of? Half dome, right? Good. You also might go home and you might, maybe not to your parents' house. I don't personally have one, but your parents might have a nice granite countertop. Right? Hit me with one of these. That would be great. Iron countertop? Expensive. Okay. This is cheap. It's everywhere. It's like what the crust is made of. Okay. All right. So this is how we define these three terms. Core, middle part, mantle. That's the medium stuff. Crust, what we stand on. Cool. Okay. You can give it other names. This was my favorite. Litho means stone. So lithosphere means stone sphere. It's the exterior of the planet. Okay. It's the cool part where we live. Okay. Everything else is the warmer, softer rock. Okay. How do we know this? Just think about this like beforehand and just put it type in. You think we got down to there?
No, but digging more and more.
Okay.
Hotter.
Yeah, definitely got hotter and hotter, and we've dug kind of far, but if you compare it to the size of the Earth, you'll be disgusted at how big the Earth is. We have not dug very far at all. But you can dig far enough that everything melts, which is sick. You just go down with a very big drill and then it melts and then you do it again. Like that's like audacity. It's fun. Yeah.
It's S-waves that we use, right?
Ah, what is that?
I don't know how to explain it, but it was in my geology class last semester.
Okay. Okay.
They use technology and they could use waves that can kind of give depth perception into the earth.
Good. All right. So let's break down a couple of things that she said. Okay, we talked about S waves, which we're going to see in a few seconds. What is the thing making them? What is the thing making those waves? No one knows?
There's one literally in the physical science building on display.
Ah, those record them, seismometers, how much shaking is going on, what causes them? We all know them very well. Earthquakes. Earthquakes create these waves that we can record all over the planet with seismometers. Okay? And they tell us about the interior. Okay, let me show you. Wait, I got it on myself. All right. First, let's do some guesstimation. Let's first learn how to read tables. And we're going to guesstimate about the interior, and then I'll show you. So water ice is about 0.9 grams per cubic centimeter. Water is about 1 gram per cubic centimeter. This is very convenient. If water ice were heavier, or sorry, more dense than water, it would sink to the bottom and things would freeze from the bottom up. Instead, they freeze from the top down like a lake. And so everything inside can survive because you create a little ice cap at the very top that insulates you from the cold air, and the water inside is perfectly fine for the fishes. Great. Good job, life. Okay. Rock is heavier than water. Not surprising. Okay. We got that one. Iron is even heavier. Okay. This is by how much? So which would you prefer to get hit by? The water ice or the iron? Water ice. Everyone wants to be hit with a snowball, sometimes a water balloon, depending on the weather, right? Okay. So let me ask you a question. If we only know about a planet, and I only tell you its density as a whole, okay? If I say to you, the moon has a density of 3.3 grams per cubic centimeter, and I use this information, I can conclude that it must be all rock, A, B, mostly rock with some iron, C, mostly rock with some water. D, a mixture of rock, water, and iron. Or E, you can't tell, bad question. Anyone else want to click in who hasn't? Okay. Okay, majority of the folks said all rock. That seem reasonable? Anyone want to defend all rock?
Yeah, I mean. Yeah, I mean, if you say it's iron, you know, all rock seems reasonable just because it's 3.3 grams, rocks around 2%, 3%. So conclude that anything higher, like say a mixture of water, iron, and rock, would be a little higher. I'm guessing I would cross that one off B as well. Mostly rock with some iron. I mean, I guess like I said it's gonna be a little heavier as well, so that's why I take that one off. And I conclude that B.
Okay, so this one you didn't like, mostly rock with some iron, because if you add this to this, it's always gonna be a number bigger than 3.7. Okay, I think that's a perfectly good argument. This one, you know, depends on what kind of rock, right? Because you could like water it down a little bit. So it seems like this one, all rock, which sits right in the middle, and a mixture, because if I use a little bit of iron and maybe some water, you get in between those, right? So it is a mixture of rock, water, and iron, but I would accept all rock perfectly fine. Okay, so that's telling you just at a glance what it could be made of. If I told you, for example, that Saturn has a density of 0.64 grams per cubic centimeter, so less than water ice, would that be surprising? Yeah, the question was Saturn's density is 0.64 grams per cubic centimeter, less than water ice. Is that weird? No, it's made of gas. It's a big boy, all gas, no rock, right? So right away, we can tell something about planets just based on one number. Does it tell you everything about the planet? No, not at all. We need more. Okay, so here's the more that we were talking about. Come on now. All right. Planet quakes, in our case, earthquakes, contain the interior. So if there's an earthquake over here, and I have seismometers over here, they will record that shaking, right? And I can use very complicated models to determine what the interior must look like. Has anyone ever seen pictures of this happening? Okay, let's hope this works. Oh wait, hold on, let me turn off my sound. Not quite. Maybe, kind of. So what's happening is you're gonna see an earthquake here. Okay, this is where it's gonna start, and it's gonna create ripples on the crust. The ground is gonna move. Now we're gonna watch it at all of these. You see each one of these dots? Each one of the dots is a weather station with a seismometer. So this weather station is gonna shake, and we can use all of that information to constrain how the crust is shaking. Okay, good. That tells you about how strong the crust is, how much it moves back and forth, how easily it moves back and forth. Then you can compare it to models, say over here, significantly farther away, and you can see, did it move just this way or did it go through a little bit? Right, here's the picture. So which one arrives first? This one bouncing in the interior, this one going through the core a little bit, right? And you can disentangle all of those signals. Now it's very hard. This is a cartoon. Let me show you the real data. Okay. Come on now. You see? So all the way out there at Alaska while these waves are going through. Cool. Yeah. You may be wondering why there's no dots in Canada. No, no, there's definitely nothing in Alaska. It's because it's American data. Yeah, it's funded by the NSF.
Why do we have?
It's funded by the NSF. So it's Americans with money going to Greenland with national American dollars. So we like to do a lot of studies in Greenland because you got big old glaciers and they're melting. And that's real bad for reasons we can talk about later. Americans want to know how bad. The answer is horrifying, but we're not going to talk about that now because we're trying to be happy. Okay. Okay, there's another thing we can check for. This is pretty fun. Just gonna let this finish. Has anyone seen Aurora or the Northern Lights? Yeah. Yeah, I had someone in Irvine send me a photo. Okay, so what does that mean? So essentially what's happening is the interior of the planet is spinning and it's creating something called a magnetic field. So for folks who have ever used a compass, that always points north. The reason for that is the basically magnetic field is coming out of the North Pole and it's going into the South Pole. So it wraps around the planet like a big torus. Okay, and it's protected. So what I mean by that is if I'm a particle, say an electron or a proton, I have charge. And so let's say I'm moving very fast. I come along, I encounter a magnetic field line, and it influences me to not hit the top of the atmosphere, but to curve and to follow these magnetic field lines until I smash into the atmosphere in this little region over here. And that's why you get called the Northern Lights or the Southern Lights, right? In a very big storm, they can extend much lower, like the one you talked about over the summer. So this is a huge storm where this material is funneled towards the poles, but it's not constrained only to the poles, it can expand, right? Depending on where the magnetic field aligns, okay? But you need three things, okay? You need the interior to be made of something that can conduct electricity. If you've ever stood outside during a lightning storm, what are you not supposed to touch? Metal, right? Bad idea. Lightning rods are made of metal. They are electrically conducting. They conduct electricity. Should you get in a pool full of water? No, very dangerous, right? Should you get in a car? Yes. Why? Rubber tires are not conductive, right? So that means that you'll be insulated because it would prefer to go through something like metal. As long as you stand in the car and you don't put your foot out, right? Then you won't die. Okay. Actually, you won't die that. Some people get really cool scars. Yeah, you should look them up. They're called Lichtenberg figures. They're awesome. Okay, convection. That's just like hot goes up, cold goes down. That's like your hot soup, right? So if you have a molten interior and it's made of metal, If it's liquid and it's made of metal and it's spinning, then you'll get a magnetic field. So you can reverse that. You can say, if I see something that has a magnetic field, then it probably is made of metal or something that conducts electricity, like liquid. For example, like salty water, really good at conducting electricity. It's probably got convection in there. Hot goes up, cold goes down, and it might be rotating if I see a magnetic field. So there's going to be places where we can't put seismometers. We can't land on the surface. But if we fly by and we don't see a magnetic field, that tells us a lot, right? Does the moon have earthquakes?
No, I won't see.
It has little tiny ones. How do we know that? It doesn't have faults. It doesn't have tectonics. But how did we find that weird information out? Yeah. We put several seismometers on the moon, right? Every time we landed, we were like, here, left it there, right? And then it just sends us information every once in a while. Right? Does Mars have Mars quakes? What happened? That was fun. Okay. Does Mars have Mars quakes?
Yeah,
Right, but the volcanoes are not active. And remember that volcanoes and earthquakes are not necessarily connected. Yeah. Right, are plate tectonics and earthquakes connected? We think of that because we think of the San Andreas Fault, but that's not necessarily the case. Tectonics is any motion of the Earth's crust. So you need plate tectonics if you want to get something like a transform fault that's like this, moving past each other, right? But if you have motion at all, you move the crust, you can shake it, right? So what happens if I smash into the surface, say with an asteroid? Wouldn't that shake the crust? And if I had seismometers, could I tell you? You can't, and you have, especially on Mars. So Mars likely has very, very little Mars quakes, but we saw recently, I think in 2022, we saw both parts of it. We saw this weird shape, and then we looked and we found where there was a new impact crater. All right. Yeah, we landed one seismometer. You can do a lot with one thing. It's more expensive to go to Mars than it is to go to the moon. Okay. So how does the world get separated into these weird things? This is going to be a new word for folks, potentially. It's called differentiation. Differentiation. So that's differences in material. Gravity is going to pull heavy stuff to the middle. Lighter stuff is going to go to the top. And it's separated by density. Any examples of this? Yeah.
oil and water, right?
Oil and water. Interesting. Interesting. Which one separates from which?
Oil goes to the top.
It goes to the top. Okay. So what would that be an example of? You have oil and water in which circumstance? Like the road? You ever notice that it's more dangerous to drive right after it rains? Oil rises above the water. Oil tends to be less dense, and suddenly the roads are slick. Whereas if you just wait a few days, that oil moves off, and even though the roads are still wet, you have better traction. Another example? Yeah.
I was also going to say something like the centrifugal force pushes the more dense parts of your mud and
Sure.
whatever to the end. So like the same can be applied to like gravity or the.
Yeah. So that's just basically making a little quick gravity thing, right? But what about an example from your day-to-day life? Saying not like a lab. Like a Friday night, maybe? No? Someone? Yeah. What's that? Oil and water. Yeah, that was the example that we had down here where they can like separate. Yeah, milk and soap also don't want to mix, right? two different densities. They want to sit one on top of the other. Okay? Folks know what this is? It's not coffee, but that's close. This is not a candle either. These are three liquids. What? This is alcoholic beverage. That's correct. Good. What's the middle one? They're all liquor, believe me. This one is vodka. I'll let you figure out what the other two are. This is a separation, and you can do this with lots of different drinks, right? So different densities exist in different liqueurs. So let's say you have one that's like water versus one that's more strong. The abundance of alcohol in that liquid gives it a different density. And because of this, you can create really interesting pieces of art, right? Where like you can do something like this, and then you drop a little bit of this material, like creme de menthe, and it creates something that looks, you know, to first approximation, like a jellyfish in water. It's pretty cool, okay? So you're taking advantage of the fact that each one of these is a different density. Which is the densest? The one at the bottom, right? This one is the heaviest per cubic centimeter. This one's the lightest. It rises to the top. Yeah.
See, it's soda, right? The syrup that makes it start trying to see close to the bottom and then just normal water flowing.
Yeah, yeah. If you wait long enough, I guess. Yeah. Let all the bubbles out, right? Yeah. Okay, so here's our three liquid solution for the Earth. This is our core, right? This is our mantle, and this is our crust. That make sense? And this is how they separate. As long as they're liquid, you'll have this type of separation. Right? If you froze these, obviously it wouldn't mix up. And so when you go to have a little bread with olive oil and balsamic vinaigrette, you have to like mix the shit out of it, right? Because they don't want to mix, right? And then you can have a little tasty bite. Okay? Okay, now here's the question. What parts of the Earth are liquid? Is it A, everything under the crust, B, part of the core and part of the mantle, C, all of the core and part of the mantle, D, just the core, or E, just the mantle? Interesting. We have three major camps here. Put in your vote if you want to vote. Okay, we have almost identical numbers of B, C, and E. So if you're in one of those three groups, try to convince everyone else around you. Okay? We're going to see if we can get everyone on one side. And if you're just guessing, that's perfectly fine. But if you read the book and you know, just tell them that, right? People know? No one read the book?
Yeah.
Okay, let's try again. Did you convince anyone or you got convinced? Click in. If nothing changed, that's perfectly fine. That it? 47, 48. Okay. No one liked this one. Some people like this one. Is anyone not guessing who wants to pick this one?
So my reasoning is the further you go into the planet, the hotter it gets,
Mhm.
right? And there's no air pressure so there's no other forms to pressure or like temperature to make everything solid again, right?
Well, hold on, let's break that sentence down a little bit. So you're saying as we head deeper into the core, there's no pressure.
I mean, what I would say is that the heat keeps it a liquid. The pressure can't outdo the heat. So
Is that
it
true?
stays a liquid.
That's true. Let's think just about water. What happens to let's say you and your billionaire best friend get into a submersible and you want to go check out the Titanic, right? Water pressure just going down several hundred meters can crush steel, right? So pressure could do funny things to us here, right? So that's a very good line of reasoning, except for we don't really know how pressure is going to play in here, right? Okay, so let's look at the interior. Okay, you have this beautiful picture. This is where we live, actually right over here in the crust, not in the crust, on the crust, sorry. Okay. So at one point it was all molten, perfectly good. And metal and rock then separate. The metals go to the bottom, the rocks go to the top. The top becomes a nice crust we can stand on. Yay, okay. The little bit that's in the middle here is the only bit that's still liquid. And it's actually surprising because in the solid center, this is due to an enormous amount of pressure, the pressure of the whole entire planet. And out here, it's cool enough to have frozen again. So you have this like weird frozen, semi-frozen region of the mantle at the top. And then the only thing that's liquid is the stuff that's taking heat from the solid core, transporting it up by convection, and then getting out through volcanoes. Right? Okay. Make sense? Okay. We have time for this. How long does it take an object to cool off? Depends on two things. Let's assume that you have two objects that you take out of an oven. Okay. Which of the two things will cool first? You want to think about how much heat was put into it. How much is it able to hold on to? And how quickly can it lose it? Yeah.
Does it depend on the size of the object as well?
Good. Yeah. So that would be the heat content. How big is the object? How much heat can it hold? Perfect. Like a plant in the audience. Okay. How do we lose heat? Yeah.
I want to say something like aerodynamics. It's like coolers have like all these spikes that don't get hit by wind and all that stuff, right?
Yeah. Something about like, okay, if we think about like a radiator, right? What is the radiator's job? It's to like get rid of heat, right? Efficiently. Your refrigerator does this, gets rid of heat. So if you ever leave your fridge door open, you're doing nothing to your house. You're actually making your house warmer because the radiator is just on the back of your fridge. So you're letting cold air out the front and hot air out the back. So don't do that. You can get in, that's nice and cozy, but don't leave it open. Okay. So heat loss, to your example, we're talking about the ability to get rid of heat in a number of different ways. Generally speaking, it's an area process. So if you look at a radiator, it tends to have a lot of very thin pieces of metal stacked very close to each other that can all get rid of heat separately. So it's an area process. Does that make sense? If I have a large area, I can get rid of heat efficiently. Boom. Okay. So the amount of heat I have is how big I am. How quickly I can get rid of it is how much area I have. Now you're freaking out. It's not math. It will look mathy, but it's not super math. Okay. All right. Come on now. So the time to heat is the ratio. Okay. If I have $100 and I spend $1 per day, when will I run out of money? In 100 days. Good. So I have something like the total amount that I have, $100, and my loss. How much am I losing per day? Tells me how long I'll have money for. Right? Okay. So what takes longer to cool? It's Thanksgiving. Very soon. We can't wait. You pull out of the oven a potato and for some reason one singular pea. Which can you eat first? The pea. Everyone knows that intuitively, right? Okay. What can you not eat first? The potato. That's going to be hot. That's when you open it, you put the butter in, right? So you close it back up. Okay. This is the same technique. The potato is larger, so it has more volume, right? And it can hold on to the heat longer. Let me show you. Okay. Volume is here. Area is here. Time to cool, how long it takes, is this ratio. If you remember your math, people remember their, I don't know if you've taken, okay. So for example, the volume of a sphere goes like the radius cubed. And the area of a sphere goes like the radius squared. And then you do some division. And the time to cool goes like how big it is. Bigger things take a long time to cool. So of the three, let's say somehow you found the most perfect turkey, that's turkey all the way through. You pull out a turkey, a potato, and a pea. Which one cools off first? The pea. Which one cools off the longest? The potato, right? Does that analogy work or no? So? Okay, let's find out. You increase the radius of a sphere. What goes up faster, the volume or the surface area? Is it A, the volume, B, the surface area, C, it depends on the starting and ending radii or size, D, they both go up the same amount. Okay, we're almost there. Okay, anyone else want to vote? All right. If you have a different answer than your neighbor, ask them why. If you don't remember volume or surface area, just type that in really quick. Yeah. I don't trust this no more.
So I mean, it does.
Okay, let's revote. Revote. Interesting, interesting. Okay. Let's think about this room for a second, right? Let's imagine that this room is a perfect rectangular solid. So you have something like the length from that side to this side, right? The width that way, and the height, right? Now let's imagine that it's a perfect cube and all the lengths are the same. If I increase the length, if I double it, how does it affect how much stuff I can put in it? Is that a bad mental exercise? Horrifying. Okay, let me ask you a different question. Look at, you see how there's these squares on the ground? Okay, you see how there's a bigger set of squares here? Not everyone can see this. So look for a place where you have a 4, right? How many do you have? You have 1, 2, 3, 4. Okay, and then there's one that's 3 by 3, and there's 9 in it, right?
Yeah.
Okay, so if I stuck one of you each, 1, 2, 3, 4, right? I could fit 9 in a 3 by 3, right? Okay. As opposed to a 2 by 2, where I can only fit 4. How many can I fit in a 4 by 4? 16. We can do squares really good. Okay. Now let's say I shrink you so that I can stack you this way as well. Okay. How many can I put in a 2 by 2 by 2? 8. I can put 1, 2, 3, 4, 5, 6, 7, 8. Right? Okay, how about a 3 by 3? 27. So I can do 3 by 3, which is 9, and I can do it 3 more times up. Okay. So what we're seeing is for volume, we have a cube. We're not just multiplying by the number twice, like for an area. But as I go to larger volumes, I go up by a factor of that volume cubed. Let me show you. Okay. Here's the R's I promised you. Volume over area. It goes like R. Okay. On the bottom is R squared. On the top is R cubed. Volumes go like the length times the length times the length. Areas go like length times the length. That make sense? No. Good. Honesty. Okay. Where should I start? The whole thing? On the math part. All right. All right. Okay. Here's the object, right? Okay. So if we imagine this has 3 dimensions, length. Now this is the other length. And this is the depth, right? Okay, but imagine that it's big. I didn't bring any squares today. You can think of this like a Rubik's Cube at home. Right? So each one of those lengths, if I make them longer by the same amount, the area gets bigger, right? This piece gets bigger, but the volume gets bigger faster. Right? So if you imagine here, I got, let's say, I started with 4 people, I could put it into 4 squares. And then by increasing by 1 square, I could add an additional 5. By increasing another square, I can add an additional, right? That rate is much faster if I can stack them on top of each other, right? If I can make it 1 foot tall. Does that make sense? That's all I'm trying to get across. Don't have to memorize how lengths work. I don't give a shit about that. Okay? What I care about is you can stack more people if you take advantage of the fact that it can be vertical, right? Volumes grow like length cubed. Areas only grow like length squared, length by length. Okay, so if you could farm, you want to be able to farm multiple places as opposed to just cows in this direction. Okay. I lose everyone? Just most people. Okay, good. All right. So the time to cool goes like the size. Because the top goes like length times length times length, and the bottom goes like length times length. And then if you divide them, trust me, it gets length. Okay. That's the bottom line. That's the takeaway message. Don't eat the potato first, even though it tastes better. Okay. Don't look at that. So, okay. There's a mathematical insight you can find in your book. You don't have to. If you want to, you can. Okay. So let's ask one question, and then we're going to talk about the interiors of the planets right before we leave. The lithosphere, that cool, hard outer layer. Sorry, let me say this again. The lithosphere is the outer cool, hard layer of the planet. Which planet should have the thickest outer cool, hard layer in terms of percent of the mantle and crust? So what I mean by that is look at the whole planet that we know about. We have different planets, right? Which one should have the thickest cold crust? Think about it for a few seconds before you answer. Should a big planet, a small planet, should it be the same no matter what? Right? Regardless of the size? Or, wait, did I just say this twice? Oh, this one says the lithosphere should always be the same fraction. And this one says it doesn't depend on size. That's basics. Ignore the last. Interesting. Okay, click in. Click in and I'm going to show you the answer. Okay. All right, here's all of the 5 planets we've been talking about. Sorry, the moon's in there. Okay, here's the Earth. That's the biggest of the 5 we've been discussing. There's Venus, Mars, Mercury, and the moon. And this is the lithosphere, the dotted line in each one of these. And you'll notice a trend, except for Mercury. The smaller planets, like Mars and the moon, have the largest lithospheres. We talked about that example earlier of how lakes freeze from the top down, right? Just imagine that if you have a big lake, then you have a lot of liquid below to keep the top very cold, right? The top can be cold, but there's a lot of hot liquid below. Where if you have a small lake, the thing can freeze all the way through, right? Okay, that's the same thing we'll talk about. And if you're freaked out by Mercury, you're paying attention. Okay, please bring your homework if you haven't done so already. And be prepared to be thinking about your check-in on Tuesday. Thanks.
Let's see.